So it's a pleasure to first welcome to this session on AI and ML, and this is part of the board of editors meeting. We thought that we can have a simple session yearly in the board meeting, and so on behalf of the editors, called the chief editors of the Sadhana, let me invite all the people, and I am very glad that very distinguished people in AI and ML agreed to give a talk. And so first speaker would be, one of the reasons is that there has been a very much hype also in the AI and ML, so that people who are working in the areas, both foundational as well as practice, it would enable us to get a picture of whatever it is. And the Indian Academy of Science is also wanting to put some of these proceedings on their Indian Academy YouTube channel, so that people can see whatever that one is, kind of a framework. And also it so happens, I looked at, when I was looking at, I didn't know what was the title we should give, and then it so happened I found that Professor R. Narasimhan, who has been one of the founding persons of computer science, he had edited a special issue for current science called the AI for Science and Engineering, and he had also written an expert. And then I thought that it is indeed nice that we thought that such a another session comes after 93 in 2019. He was the founding of the Tata Institute of Fundamental Research, Professor R. Narasimhan. So in that sense, he made a lot of infrastructure building for the computer science. It was nice to see that he had done already one volume under the Indian Academy of Science, and now we are having. I'm very glad to have Professor Dr. Rajiv Rastogi. He is a ACM fellow. When at a young age he became an ACM fellow, that speaks for his creditability. And he is the director of the machine learning. And while talking, he also mentioned that he did an undergraduate thesis, BTech in IIT Bombay, with Professor G. Nagaraja, and it seems I was the examiner for the BTech. So it is indeed nice we meet after a long time, Professor Rajiv Rastogi.
It's an honor to be here today, talking here, so thanks a lot for the invitation. And yeah, you may not recall me, but as a young student, I remember you very clearly. I had even come down to TIFR. So when you invited me, it was, I was very delighted to accept the invitation. I am part of the India consumer business of Amazon, and I, will talk today about how we are using machine learning to, innovate for solving business problems that, we encounter as we roll out e-commerce and do online shopping and things like that here in India. So I just want to start with a short video of the Amazon CEO, Jeff Bezos, and some other senior leaders talking about different applications of AI. Some that are a little bit futuristic, but it kind of tells you about the various possibilities that AI will enable in the future. So let me just play this.
I think natural language understanding, I think machine learning in general, artificial intelligence, probably hard to overstate how big of an impact it's going to have on society over the next 20 years.
The vehicle is completely autonomous. It lands by itself, it navigates by itself. It can fly more than 50 miles an hour, it has a 20-mile range.
We're really just beginning in robotics. It is the birth of robotics right now. We use our machines at Amazon so that we can have a more efficient fulfillment process. Ultimately, it's about humans and machines collaborating together in order to achieve a meaningful task.
Alexa, add anniversary to my calendar.
Alexa, accept the call. Hey, Mom.
Alexa, play my relaxing playlist.
Alexa, turn off the lights.
Okay.
So with Amazon AI, we're bringing the power of deep learning and advanced machine learning to all developers so that they can bake intelligence inside the heart of every application and inside the heart of every business.
Recognition allows you to pass an image to us, and we will detect objects in an image. We'll be able to tell you that there's a person in this image, or it's a woman in this image, or it's a car.
With A9, we're completely reimagining what it means to search. From landmarks to books, visual search enriches the world around you with contextual information powered by artificial intelligence.
Today, we don't have any if conversation. Every conversation is a when and how conversation. This is a world that I want to live in.
Okay, so that sort of talked about a few applications, some of which are already there, things like Echo and so on, and of course drone-based deliveries and robotics. There's still a long ways to go. So here's sort of the outline of my talk for this afternoon. I will give a brief introduction to machine learning, and then I will talk about different applications of machine learning that we are developing at Amazon, and I'll conclude with some of some big AI challenges for the future. So there are many types of machine learning methods out there. In supervised learning, training examples are labeled. In unsupervised learning, your training examples are unlabeled. There are two main types of supervised learning problems, classification and regression. Classification, your target labels take discrete values. Regression, your target labels take continuous or numeric values. And then there's a whole area of unsupervised learning where you're clustering examples so that similar examples are assigned to the same cluster. Dissimilar examples are assigned to different clusters. And more recently, there's a lot of interest in reinforcement learning. You've heard of AlphaGo, where a program beat the Go world champion. So there's many other applications besides game playing for reinforcement learning. And in reinforcement learning, your model predictions are driving real-world actions. And each action has an associated reward. For example, in online advertising, your models predict ad click probabilities, which are then used to determine the set of ads that you show to the user. And this is the action. The user click on those ads are the rewards. And what reinforcement learning techniques try to do is that they try to maximize long-term rewards. If you look at supervised learning, there are, these algorithms have two main phases. In the training phase, you're given these training examples, xi, yi. Xi is a feature vector, and I'll give some examples of features. Yi is the target variable that you're trying to predict, and the learning algorithm learns a function f that best fits the training data. And when I say best fits the training data, what I mean is yi is approximately equal to fxi for all the examples I, right? And f here is what we call a model. During the prediction phase, you're given a new example that you've never seen before, with an unknown y, and you're going to try and predict what y is using fx. So here is an example where we have a web page. We take different features of the web page. It could be the URL, it could be text in the web page, hyperlinks. These are input to the model F, and the model makes a prediction whether the web page belongs, is an e-commerce, belongs to an e-commerce site or not. Okay, during the training phase, we saw that what we do is we learn a model that best fits the training data. More formally, we select F so that a loss function L on the training data D is minimized. And intuitively, what this loss function is doing is it's capturing the difference between the actual target value and the value predicted by the model. And the bigger this difference, the larger is the loss function value. And There are many possible loss functions out there. The most intuitive and commonly used loss function is squared loss. It's the square of the difference between the actual target value and the predicted target value. And with squared loss, you get linear regression models. Logistic loss is a popular loss function for classification problems. From the expression, you can see that logistic loss tends to 0 when the actual target value, which is y, which takes values +1 or -1 depending on the class, and the predicted target value fx have the same sign. Okay, so this quantity becomes close to 0. So since we're trying to minimize the loss function, the logistic loss forces the actual target value and the predicted target value to have the same sign. And similarly, there's another loss function, hinge loss, which is also popular for classification problems. You can see again that hinge loss is non-zero if the actual target value and the predicted target value have opposite signs. So hinge loss also forces the actual target value and the predicted target value to have the same sign. So going a little bit more into what these different forms of this function f can be, f can take a linear form, and then you get linear models. So you can see for linear models, fx is nothing but a dot product of the weights vector and the features vector. Here's an example where fx is a weighted average. You're trying to make a forecast for future demand forecasts. You can take a weighted average of the 1 month and 6 month demand. And during training, what you're doing is you're learning these weights W to minimize this loss function, which popular loss function again here could be squared loss. Now, linear models are trained using learning algorithms like stochastic gradient descent, and these scale to large number of features and training examples. The objective function to be optimized for linear models is convex. So a lot of the gradient descent methods converge to the optimal solution. They're also easy to interpret. That's another benefit of linear models. The importance of a feature is nothing but the weight that you learn for the feature. The disadvantages of linear models is that they have limited expressive power. Specifically, they cannot capture complex nonlinear relationships between the features and the target value. Now, decision trees are another popular class of models. Each internal node specifies an attribute and range of values to partition the data. And then you have these leaf nodes that are associated with class labels to make a prediction for a new example. Starting with the root, the attribute split condition is applied to the example at each node, and the example is pushed down to the child node associated with the satisfied condition. Once the example reaches the leaf, the predicted value is the class label associated with the leaf. Decision trees have a number of desirable properties. They are easy to interpret. You can actually, a root to leaf path is a conjunction of attributes, so you can explain your predictions. And they also can model complex nonlinear relationships between the attributes and target values. So in that sense, they're more powerful and more expressive than linear models. A drawback of decision trees is scaling them to a large number of features and training examples. So if you have data like that's text data where each word can become a separate feature, it can be challenging to use decision trees because a lot of these algorithms load the data into main memory and then work on them. Another shortcoming of decision trees is that they tend to overfit the data, so you may get very, very different trees on different training examples. And one way to reduce variance here is to learn an ensemble of trees, and that's where gradient boosted trees come in. These learn an ensemble of decision trees. Each subsequent tree is trained with higher weights assigned to previously wrongly classified examples, And to make a prediction, you combine the predictions of the different trees. Now, combining predictions of multiple trees helps to reduce variance. Gradient boosted trees also have higher prediction accuracy. That's what we found compared to a single decision tree. Of course, some of the drawbacks here are they're difficult to interpret. You have now a tree ensemble. There's also more expensive to train because you're building multiple trees. Now, deep neural networks have multiple hidden layers. Each of these layers learn higher level features. Each layer applies a nonlinear transformation to features from the previous layer to learn a higher level feature representation. The nonlinear transform is typically a sigmoid or a logistic function. And now, by stacking many of these nonlinear transforms one on top of another, deep neural networks are able to model highly convex and highly non-convex and complex functions pretty efficiently. Now, one problem with deep neural networks, which is again a popular area of research today, is how do you provide explanations for predictions? How do you make that? How do you make DNNs more interpretable? And of course, a key challenge here, as I mentioned, DNNs can model highly non-convex functions with multiple local minima. So, your algorithms like backprop can get stuck in a local minima, and this can slow down convergence of algorithms. So, this slide here shows features that are learned at the various layers of a deep neural network that's trained on images of faces. You can see that the first layer, the DNN learns edge features in different orientations. In the second layer, it composes these edges to learn more complex features, such as different parts of a face, for example, eyes, lips, noses, and so on. And in the third layer up here, it composes these features to learn even more complex features, such as face shapes of different persons. Okay. So what's happening in different layers of the deep neural network is that you're learning higher level feature representations. So that was the outline, but I'm just going to move on to talking about applications of machine learning at Amazon, and there are literally many, numerous such applications. And I'll touch upon some of the applications today. We are using machine learning to improve the experience for our customers and sellers, and also the quality of our product catalog. We're also applying machine learning techniques to diverse types of data, such as text, images, and speech, and you can see some of that at the bottom there. There's some fairly mundane applications. We are using machine learning to determine the most cost-effective packaging to use for a product that leads to the least damage. So here you can see the different packaging types for a product, and this is an increasing order of cost, and you've got to sort of balance the likelihood of damage with the cost of the packaging, right? So you're using machine learning to predict damage probabilities for a given product and a packaging type. And again, this can have a huge impact on costs of packaging and also the environment, because the lesser packaging we use, the more environmentally friendly it becomes. We're using machine learning to identify substitutes for a product, and products that customers browse in the same session but don't purchase together are good candidates for substitutes, because when you buy a product, you're typically looking at a number of other substitute products, but you end up buying only one of them. And we show low price substitutes to customers, or show substitutes to customers when a product is out of stock. Amazon has been a pioneer in the area of recommendations. We proposed collaborative filtering algorithms way back in the 1990s, and most of you have probably seen the customers who bought this also bought widget on the Amazon product page. This is powered by highly scalable data mining algorithms that compute frequent co-purchases. We also learn about customer preferences from their browse and purchase history, and then recommend products to customers that match their preferences. Our catalog here in India has close to 200 million products. A key challenge for us is classifying those hundreds of millions of products into our product taxonomy, which has over 50,000 leaf nodes. So this is a pretty massive multi-class classification problem. And customers browse through our product taxonomy to discover products. So accurate product classification is key to product discovery. So here you can see this particular product is this is the root to leaf path in our product taxonomy. It comes under jewelry, women, bangles, and bracelets. So now, when multiple, we run a marketplace here in India. So when multiple sellers list the same product, we end up with duplicates in the catalog. So you can see these product listings. They all correspond to the same real-world product, but you can see that the images are quite different, and even if you look at the titles, they're quite different. So this problem becomes fairly challenging, and identifying and eliminating duplicates from the catalog is critical for certain applications that we have. For example, in search, we don't want to show duplicate products in search results, because that can lead to a poor customer experience. You wouldn't want to do a search and then see out of the top 10 results, 5 are duplicates. We're also, on the tech side, we are working on extracting fine-grained ratings for product attributes from reviews. And this requires natural language understanding and sentiment analysis techniques. So here I've shown a screenshot of the DP Reviews website. This is a website that specializes in cameras, and they give you fine-grained ratings for different camera attributes. Here, for a Panasonic camera, they've got different dimensions like image quality, video quality, and so on. All this is generated manually by experts. So we want to automatically generate these fine-grained attribute ratings by extracting them, all this information from reviews, because we already have a lot of reviews data, and all this information is contained in them. But it is challenging and involves natural language understanding to understand what's the sentiment that users have expressed. And there's, of course, different ways of referring to a given attribute, sound, audio, and so on. So now let me dive deeper into a few applications in the rest of the talk. So can I just get a little bit of water here? Now customer address is the single most important input to deliver a package to a customer. Addresses in India, as you know, are highly unstructured, and there's no golden reference database containing all the legitimate or locatable addresses like other countries have. If you go to the US, there's actually a central database, and every address that's a legitimate address is contained in that database. MapMyIndia and India Post Service address databases are incomplete. And these are real addresses that people have typed on Amazon. In many cases, people enter fake or non-existent addresses because they have no intention of receiving the product. This could be to get competing sellers to incur some delivery expenses, or even to exhaust the inventory of competitors. Incomplete addresses, again, hurt the productivity of our delivery associates. Our DAs are required to call the customers to locate the address, and you have spelling errors and missing spaces that again make it very difficult to tokenize an address and locate the address. Now, to correct addresses with spelling errors, we employ a noisy channel model. So a correct address here is input into a noisy channel. The noisy channel introduces noise or spelling errors into the address, and the address with spelling errors is then output from the channel. Now, given a misspelled address with spelling errors, which is X here, we can recover the original correct address, W, by selecting the address with the highest probability shown here. Now, you can apply Bayes' rule and rewrite this as the product of these two probabilities. And intuitively, what this equation is doing is that it's considering all addresses, all Amazon customer addresses to which we have successfully delivered packages in the past. That's captured by this language model here, and then from among those addresses, we select the address that is closest in terms of edit distance or some other distance measure to the misspelled address. So this address is most likely to have generated the misspelled address. And the likelihood of the misspelled address given the original address is captured by the channel model here. Okay? So running our spell correction algorithms on these input addresses, you can see that, Worley, Woolwich, a lot of these spelling errors got corrected, and also, this thing got broken up by introducing spaces at the appropriate locations. Now, to identify incomplete and poor quality addresses, we've come up with the notion of address and address quality score that for each address, it captures the degree of completeness for an address. And, as you make this address more complete, the address quality score becomes higher. So you can see, just an address, Malleswaram West, without any building name or street name, has a very low address quality score, and we suppress such addresses and don't even attempt delivery for addresses with very low scores. And as you can see, as you add the building name, street name, floor information, and so on, the address deliverability score keeps increasing. So how do we compute this? It's fairly simple at a high level. For an input address, we first retrieve all similar addresses to which we have successfully delivered packages in the past. We use k-nearest neighbor search algorithms like locality sensitive hashing and so on. And the ADS for the address is then the average similarity between the address, the input address, and its k-nearest neighbors. And you can see that this particular address here has a score of around 35. A number of our customers don't input the address type, in this case, a residential or a commercial tag associated with the address, and knowledge of the address type helps us to improve delivery success rates by not delivering to commercial addresses on Sundays, and it also helps us to improve delivery speeds by delivering to residential addresses on Sundays. And here again, you can see that the address string is input into an LSTM model, and that predicts the type of the address. And the LSTM model can distinguish pretty similar addresses. This is this is where our office is in World Trade Center, but then there are apartments right next to it, and the model is able to distinguish between those two addresses. Address geocodes are again are important because they help us locate addresses on maps, and this improves again efficiency of our DAs. It also helps with routing, coming up with efficient routes and so on. And our approach for computing address geocodes is to leverage geocodes for addresses to which we have successfully delivered packages in the past. So for each address token, we compute a geocode. And this is the mean of geocodes for all addresses that contain that token. We also compute an error radius, which again is derived from the variance of geocodes for addresses that contain that address token. So you can see here that address tokens that correspond to localities like Marathali have a much higher error radius compared to address tokens that correspond to building names, which have much smaller error radius. And now when you get a new input address for which you want to get a geocode, you combine the geocodes for the different address tokens by taking their weighted average, and the weight here for each address token is inversely proportional to the error radius. So here you can see we can get a new address. It combines all these geocodes for these address tokens, and it weights them inversely based on their variance or their error radiuses. And so the most weight does go to this particular token, and this is where you locate the address. Now, let me talk a little bit about some work we've done on question answering. Now, Amazon product pages contain a wealth of information. Product descriptions contain information about product specifications like battery life, camera megapixels, and so on. While customer reviews shown here capture user feedback and sentiment about different features. We even have customer Q&A data that contains authoritative answers to customer asked questions. These are typically open-ended questions about people's experience with using a product or how a product compares with other products. Now, the average product page for the top 20 best-selling products across categories at Amazon contains over 4,000 words. So you can imagine that finding information can be quite challenging, especially if you have a smartphone. So to make it easy for users to find information that is embedded in product descriptions, customer reviews, community Q&A, we've implemented a question answering interface on our product pages. Here is a screenshot of the text interface to ask questions. Now, a majority of product questions are about product features like battery life, camera megapixels, and so on. These can have factoid answers that can be directly extracted from product descriptions. So for example, here you have a question, how heavy is it? And this question has a factoid answer, which is 8.6 ounces. Or these questions can have more subjective answers that are available in product reviews. So for example, the question, is this camera expensive, has the following answer that's extracted from a customer review for the price. This is good value for money for an amateur photographer. Now, one thing to observe here is that these snippets containing the answers for the questions do not have high text similarity or high text overlap with the questions. So, for example, here the question has the word heavy, but the snippet has the word item weight. Similarly, here the question has the word expensive, but the snippet has the phrase value for money. So what this means is we have to do semantic matching between questions and snippets. Another popular category is product comparison questions. So these compare two products with respect to certain features. So how does here's a question, how does it compare with a Rebel SL1? So it's about comparing two cameras. Well, it's more compact and the specs are not as good. So and then there are also product compatibility questions. Does this camera work with Canon lenses? And here's the answer contained in the product descriptions, that it is compatible with all of Canon lenses. So a key challenge here is really understanding the semantics of questions. The question, what is ISO, refers to the definition of ISO, but the question, what is the ISO, refers to the ISO value of the camera. So just the word "the" completely changes the semantics of the question. As we saw earlier, we need to perform semantic matching between the question and snippets, since there may be very few overlapping words between the question and the matching snippet containing the answer. This is because customer questions and review snippets can refer to a product attribute like price in multiple different ways. Cheap, inexpensive, bang for the buck, and so on. Matching these different variations of meanings requires semantic matching. We would like to generate natural language answers to questions. For example, a question, is this expensive, could get an answer, this is great value for money. We also, in order to ensure a superior customer experience, we want to answer questions with a high degree of precision. The systems that we have launched in production have a precision greater than 90%, just to make sure that customers trust our question answering systems. Also, as we saw earlier, users can ask a wide range of questions. The data required to answer some of these questions may not be available in product descriptions or reviews on the product page. So for example, we may not have data really to answer this question, will this suitcase fit in the overhead of an airplane? And finally, the data that's there in product descriptions and reviews that are used to derive answers may not be accurate, and this can lead to incorrect answers. So, to find these semantically matching snippets for a user question, we learn joint embeddings of questions and snippets, so that semantically related questions and snippets have embeddings that are close. Embeddings are nothing but mappings to a high dimensional space. Now we learn these embeddings using a Siamese neural network that is trained on question, relevant snippet, irrelevant snippet triples. We obtain these training examples from our community QA data. So the question answer pairs become question relevant snippet pairs, and we get those irrelevant snippets by taking random answers from our community QA data. Now you can see here, here's a question: is it expensive? A relevant snippet is product is very good for the given price. An irrelevant snippet is autofocus is great, which has nothing to do with the price of the product. Now, word embeddings of the question, relevant snippet, and irrelevant snippet are fed into 3 separate RNNs that learn sentence embeddings for each of them. Now, these word embeddings are learned are computed using Word2Vec, and Word2Vec essentially finds vector representations for words that is based on contextual similarity. And the question embedding here is then combined with each of the snippet embeddings in an additional layer on the top that outputs either the probability that the snippet is relevant to the question. So this is modeled by a logistic function applied to the dot product of the embeddings, or it can output the cosine similarity between the two embeddings. And we consider several different loss functions to compute these question and snippet embeddings, so that questions are embedded close to relevant snippets. The first loss function is log loss or cross entropy loss. So it's the negative log of the product of probabilities of the relevant and irrelevant snippets. The second loss function is Siamese loss or triplet loss. And what this loss function tries to do, and this is this loss here, it tries to maximize the margin between the cosine similarity scores of the question with respect to relevant and irrelevant snippets. So the loss function imposes a penalty if the difference in cosine similarity scores exceeds a certain threshold m, but once the difference between the loss function gets higher than m, then the loss function value drops to 0. So we use this precision at rank 1 metric to measure the performance of the different loss functions, and our baseline here is standard cosine similarities. So it's a text-based metric. So you can see here that a simple text matching approach that's based on cosine similarity actually performs quite poorly. It has a precision at rank 1 of only around 57%. But using a semantic approach that learns embeddings using these loss functions gives a much higher precision at rank 1 score of almost 96%. So that's one takeaway, that semantic approaches do make a difference in terms of relevance. The second big takeaway is that you can see that different loss functions, log loss and Siamese loss, have very different performance. So the choice of loss functions does matter. And here are some qualitative results from our for our question answering system. As you can see, our question answering system returns semantically matching snippets for the first 4 questions here. For example, it figures out that the keyword basketball here in the first question is semantically related to the keyword sports. Similarly, the snippet on item cost is semantically matching with the question, what is the price, and item dimensions, again, matches with how big is it. Also, stabilization is semantically related to blurry. Of course, our question answering system does make mistakes. So for example, a question like how much weight can it hold for a camera tripod is misinterpreted, and the system returns the item weight. So it just says what the weight of the tripod is as opposed to the weight that it can hold. So again, it's more complex semantics there and probably requires more advanced natural language understanding techniques. Let me talk a little bit about work we're doing on improving catalog quality. As I mentioned earlier, our catalog has close to 200 million products with a range of attributes like title, image, description, and so on. And it's very critical for us to ensure that the information contained in these attributes is factually correct, because many of our customers make purchase decisions based on these attributes. Also, the information needs to be consistent across the different attributes, and the information needs to adhere to certain preset guidelines that we have. As I mentioned earlier, we operate a marketplace here in India, so many of the sellers, since sellers are responsible for populating the metadata for products, some of the product listings end up having defects, and these poor quality listings can erode customer trust. It can hurt sales and conversions of products, and also lead to excessive returns, which is all not so great for our business. So we use machine learning extensively to identify and fix various defects that we find in our catalog, and also to do this at scale, when you're doing it at a scale of hundreds of millions of products. So here are some examples of defects. So here is a product listing where the title is too long. There's also all sorts of spam keywords like Bollywood and latest design and so on that sellers have inserted into the title, presumably so that it shows up in search results, and their listings can get more sort of impressions. There's also cases where people have put email IDs in the product title, which again is against our guidelines. Here you have product images. Again, when you're shopping online, really the catalog is what you have. You can't see the product. You can't, don't have anybody to talk to. So what you see on the catalog is what you're going to use to make your buying decision. So that's one of the reasons we are very particular about, the format of the titles, the way the images look. So you can see here, we require the backgrounds to be white, and we don't want these other objects showing up. So, and here the product image is cropped. It doesn't show the complete product. It's very difficult for a a customer or a buyer to purchase a product which, which they don't know how it's going to fit or how it's going to look. There's also, defects where there are mismatches between the attribute title and the image. So here you can see that the title says that the product is a T-shirt, but the product image shows a bag. So if you order this product, you aren't sure what you're going to end up getting. You could get either a T-shirt or a bag. Similarly here, the title says that the product is blue, but the image shows a pink dress. So here again, you don't know which color you're going to end up getting. A key capability that we need to identify and correct such defects is the ability to extract attributes from like brand, color, size, model from text attributes like titles and descriptions. So for example, we want to be able to extract that Dustin here is a brand, transparent black is a color, and we use deep neural networks for this. The product title is input into a multi-layer deep neural network with multiple layers, and embeddings that are generated by this bidirectional LSTM layer here are input as features into a CRF layer that outputs labels for the different words in the title. We also need the capability to detect defective images, extract color and other attributes from images, and also classify images. So for example, we need the ability to predict that this product image here has poor quality. We want to be able to predict that this image here contains a maroon dress, and that this image here is shows a T-shirt. And here we use deep convolutional neural networks to learn image representations or embeddings that are then input to machine learning models that perform different classification tasks. So once we have extracted attributes like brand, color, category, and so on from the title and the image, we compare them. If the extracted values don't match, then we notify the sellers that they have to go ahead and fix the product attribute mismatch defect. Whoops, what happened here? Okay, yeah. So one final application, and then I will jump into some of the big AI challenges. We also use machine learning to forecast the future demand for a product. These demand forecasts need to be extremely accurate because if we forecast the demand to be too high, then we are going to be stuck with excess inventory that we may have to liquidate, or there's cost to storing that inventory. And if we forecast the demand to be too low, then the product goes out of stock, and that's not a good experience for customers, for them to come to Amazon and see that a product is out of stock. A major problem here is data sparsity. It's the Zipf's law. Most products sell very few, don't get purchased a whole lot. There's a lot of skew in the data with a long tail of products that sell very few items. So all these products here you can see have very few sales. There are some products like phones that have huge number of sales, right? So, and then demand for some products exhibits seasonal patterns. So for example, there is swimsuits sell a lot more in the summer months, while there's more demand for sweaters in winter. Our models need to capture these. There's also demand spikes due to external events, like for instance, if there's a launch, or you have Diwali or Christmas or Valentine's Day and so on. Or there could be unforeseen events like a snowstorm that leads to a sudden spike in snow shovels. So we're again using a sequence-to-sequence model for forecasting the demand for products, the past historical demand for the product, along with other product features like the product title, category, maximum price. These are all fed into the encoder portion of the model, and the decoder portion of the model outputs the the demand, the future demand across different time horizons. Now, most machine learning models out there generate point estimates corresponding to the average demand. However, what we require here are probability distributions over the demand, since these demand estimates are used by our inventory management systems to place product orders. Our systems order products based on the 90th percentile of demand, and this is to ensure that the products are in stock 90% of the time that customers come to Amazon. And here we use a quantile loss function to generate the different quantiles for the product demand. So in addition to doing future demand across different time horizons, we also generate quantiles for every time horizon. So let me just conclude with just talking about a few big AI challenges, AI problems that we are working on. So we're working on building a conversational shopping engine that would interact with users similar to a shopkeeper. And the motivation for this really is that a large population in India, once you go to the tier 2 towns and villages, they aren't very internet savvy. They're not familiar with online shopping and searching and those paradigms. What they are familiar with is talking to a shopkeeper to purchase something. So the objective here is to build some sort of a conversational shopping bot that would guide users to the product that they're looking for by refining the product requirements at each step of the conversation. So here you have a customer, she says she wants a phone, and our shopping engine tries to narrow down her requirements in terms of price to price range of 5,000 to 8,000, and also the brand and so on, so that the goal here is again to do exactly what a shopkeeper would do in terms of getting a customer to buy a product, right? And again, it's more really motivated by the fact that if you want to get beyond the first 100 million users in India, you have to have a different paradigm that perhaps in terms of vernacular languages, shopping conversations, and so on. So again, this is about expanding reach for Amazon to tier 2, tier 3 towns, and also going into the rural villages and so on. A big challenge is really around automatically generating content. So one challenge would be to automatically generate a Wikipedia page on any topic, right? So if you had great content summarization technology, then you could do this by taking any topic, doing a search on Google, retrieving the top 100 web pages on the topic, and then summarizing the content in those web pages to automatically generate a Wikipedia page on that topic. So again, the big challenge here is really how do you do very high quality content summarization, human-like content summarization. Of course, there's a lot of work going on in terms of generating captions for images. The next frontier there would be video. Could you take a movie and generate an expert review for the movie automatically, right? So that would be definitely stretching the limits for AI. I talked, the video alluded to a number of efforts in the area of robotics. Our fulfillment centers that Amazon builds, these warehouses are the size of multiple football fields. Manually transporting products from shelves where they're stored to the packaging area would require humans to cover extremely long distances. So what we've developed are these Kiva robots, and you saw them in the video. They automatically transport products from shelves where they are stored to the packaging area where the products are sorted and packaged for an order. We're also developing robots to pick products from shelves and store them in these yellow containers that are then transported by the Kiva robots. And it's very easy for humans to pick objects, but it's extremely difficult to get a robot to do exactly the same thing. So that's something that we're working on. And of course, our drones use computer vision techniques to recognize objects and patterns. And this is extremely important when you're delivering packages to people's homes. You want to do these in a manner that doesn't hurt somebody's pet or somebody's little child. You can't have the drone just land on a pet or something. So the drone needs to have some level of computer vision to at least know that there's no object like a pet or a small child where it's delivering the package. And finally, today there's personal fitness devices, there are sensors in homes, and all these sensors are generating massive streams of data, measurement data. So, here you have streams of data containing heart rate, BP, and blood sugar measurements. You could have streams of temperature, humidity, and so on. And we need the capability to analyze these massive data streams if we are to detect if somebody is having a heart attack or if there's a house that's on fire. And for this, we need online algorithms for anomaly detection, for training machine learning models like linear models, gradient boosted trees that I talked about, or identifying the nearest neighbors to for incoming points. So with that, I'm going to just conclude. We're using machine learning pretty extensively. It's at the core of our business. And of course, deep neural networks are being used a lot to learn higher level feature representations for applications like question answering, catalog quality, and so on. And there's a number of very tough problems, AI problems, still that remain to be addressed around conversational systems, content summarization, robotics, summarization of videos, and so on. So with that, I'd like to conclude, and if people have a question or two, I'm happy to take them. Yeah, we do do image recognition to detect fake logos for Nike and things like that, because many times. I see, yeah. So we do have technology that we are using, machine learning for fake reviews, counterfeit products, where we try to.
But do you act on them, or do you act on them?
Yes, we act on them. We will check out sellers from our platforms that are selling counterfeits, and we will ban reviewers that are putting in fake reviews. So that's one of the problems with crowdsourcing. I think but there's so many different websites where, if you look at Yelp, TripAdvisor, where people make a lot of decisions based on reviews and the feedback that, and anytime you have a system where, ratings are determined by people, what people say about a product or a, restaurant or a hotel, people start gaming the system. So, they're going to try and employ armies of people to put in positive reviews. They even do things like give negative reviews to your competitors so that your business does better. So we have all of that going on all these sites. And of course, we put, that's one of the big applications of machine learning. Yeah.
How accurate are your demand forecasting methods given that there is a skewness, there's no power law in the data?
Yeah. I mean, it can. This is not an easy problem. You can have 50% error on many of these forecasts. I mean, there are products that would just sell one in the last year. How are you going to predict accurately, right? So it all depends. I think when you talk about products on the head, where there's a lot of sales like phones and things like that, those can be predicted fairly accurately. But new products that have no historical demand or products that have very little history, of course, we use features, lots of features of products, like for instance, where you're trying to make a prediction for a phone, a new phone. We'll look at, how much is the RAM, how much is the camera megapixels, and so on. So we try to use a lot of the features to try and make, and that makes a difference, yes. We are able to, do pretty good, yeah.
Yeah, my question is about the Alexa thing, that conversation that you sold.
Right.
There is a possibility that a child can go into a conversation, and Alexa can be lured to accept the order on behalf of somebody, and then Amazon lands up with a kind of a fake order. So this conversation thing, I am not very sure that what kind of safeguard that you should kind of put them in the system, conversation system,
Right.
so that it doesn't really do that kind of a damage.
Yeah, I don't really know what checks and balances we have in the product, but it wouldn't be very difficult to do speaker recognition and only allow. We already have technology to identify speakers, so people can just declare that these are the speakers from whom you accept orders. So if a child spoke.
Voice recognition itself is questionable.
What's that?
Voice recognition system itself is questionable. In that sense, I can fake somebody's voices, right?
You're saying you're going to record somebody's voice. I thought your question was a child would speak. Right.
I can also fake it, like mimic.
You try to mimic a voice. Yeah. But then, somebody can break into your account and then place a lot of orders. We deal with that already. In fact, we deal with problems where the kids have access to the account and they've ordered stuff that the parents didn't know about. So we are dealing with a lot of those things. It doesn't take Alexa for those problems to come up. Yeah.
How are you handling natural language in languages besides English? Because if you talk about tier 2 cities and people who don't know how to use your web system, then they may want to place an order in Bengali or Marathi or something.
Yes.
How well can Alexa handle those?
Again, that's all work in progress, but I think voice recognition technology is pretty amazing. My dad can't hear, and the way I talk to him is I speak to a Android phone, which translates it into text, and then he looks at it and he responds. So, and this is something that I just started using, and it could actually translate things pretty accurately, and it worked. So voice recognition has come a long ways. I think if you use Alexa, you'll see that it actually does very well, and that's why it's so successful.
Thank you.
On a lighter note, conversational shopping engine, does it also give bargaining experience? That's what probably the tired aerospace market.
Right. Yeah, we'll have to put that in. If that's part of the culture, we'll incorporate it,